I'm going to show how to design a differential amplifier. So basically, there will be several steps. Our first step is to calculate and estimate the parameters, basically the W by L ratio for all the transistor, and then we are going to simulate it by using the Cadence Virtuoso. After that, we are going to plot and check our estimated gain or all other parameters. So if I show you the specification for our design amplifier, basically you can see here the VDD is 1.8 volt, the slew rate is 20 volt per microsecond, and the gain bandwidth product is greater than 20 megahertz, and the load capacitor is 4 picofarad. Our estimated gain will be greater than 30 dB, and maximum ICMR is 1.2 volt, and the minimum ICMR is 0.75 volt. And ignore this parameter because we are going to extract those parameter, basically the mu n Cox, mu p Cox, maximum threshold voltage for the NMOS and minimum threshold voltage for the NMOS and maximum threshold voltage for the PMOS. We are going to extract those parameters from the cadence because we don't know uh, those values. So our first step is to calculate the current which is basically flows from the M5 transistor, basically this tail current. So we are going to calculate it from the load capacitor and the slew rate. So our load capacitor is 4 picofarad and our slew rate is 20 volt per microsecond. So our estimated current will be 80 microampere. Then we have to divide it by 2 because the half of the portion current will be flows from the M3 and, and the M4, M3 and M1 transistor, and other half current will be flows from the M4 and M2 transistor. So if I'm going to divide it by 2, then the current will be 40 microampere. After getting the current, I have to extract the values of mu n Cox and mu v Cox from the cadence. So how to do that? To extract the NMOS parameter, I have to set up this arrangement here in a upper region. I put here a current source, the above, and for the PMOS, I have to set a current source in below. Then I have to set the current. If I show you that, which is basically the 40 microampere, and also I have to ensure that those transistor will be working in a saturation region. So that's why I short the drain and source. As it is a direct connected load, the transistor will be works in a saturation region. Then I launch the ADL and set the DC analysis and save the DC operating voltage. Also I set the VSS is 0 volt and VDD is 1.8 volt. After run the simulation, to extract the mu n Cx and mu p Cx parameter, there will there will be several methods. The first method is to uh, know I have to know the VGS, gate to source voltage, and the threshold voltage. And as I know, there is another thing. Then I have to say the W by L ratio, W by L parameter, that to neglect the channel length modulation effect. Here I set the maximum length and width, which is basically the 10 micro. So set the maximum length and width to for neglect the channel length modulation effect. After set, if I annotate the DC operating point, you see here the gate to source voltage, and but here is no threshold voltage. To show this threshold voltage, I have to set up for NMOS is another field. I have to VTH. For the PMOS, same. You can see the threshold voltage is 353.89 millivolt. Also, here I get the gate to source voltage, which is basically the 834.43 millivolt. So here I get the gate to source and the threshold voltage. If I get all the parameters, what we know that in a saturation region, ID equals to 1 by 2 mu n Cox W by L, then V gate to source VGS minus VTH whole square. Here I know the current, which is basically the 40 microampere, W by L, which is basically the 1, and gate to source and threshold voltage I know. Then I easily calculate the mu and Cox value. So mu and Cox, here I calculate the mu and Cox from those parameters. Also I calculate the this is basically the mu pitch Cox. Also in a second method, this is also an easier method. As we know, in a cadence there is a parameter which is called basically the beta effective. B effective equals to mu n Cox into W by L effective. So if I know the W by L, or I can divide it by W by L, I easily calculate the mu and Cox. So how to know the beta effective from cadence? After run the DC analysis, you have to result and then print in a DC operating point, then click the NMOS. You can see here is the beta effective, which is basically the 357.55. So here I put the value 357.55, and the W by L is 1. If I divided this value by 1, then here I get the mu and Cox. The 357.55. So here I put the value 57.55, and the W by L is 1. If I divided this value by 1, then here I get the mu and Cox. Also, if I click this MOS, then you get the beta effective for the PMOS PM0, and this is the beta effective, which is basically 234.53. So this is basically the mu and Cox value for the PMOS. After that, estimate the value. I randomize this value. So this is by 353 and 235. So I get the mu and Cox and mu p Cox. The next step is to calculate the W by L ratio for the M1 and M2. How to calculate that? As we know, the GM equals to 2 pi GBW into CL. So if I calculate the GM, which is basically 502.656, so GM equals to, here you get that the GM equals to here you can see the GBW CL into 2 pi. So our GM is 502.65. If I get the GM, the W by L equals to GM square into 2 into I into mu and Cox. So I3, uh, I means which current flows from the M1 MOS. So which is basically flows from M3 M1. Then this is basically the 40 micro. So I know the current. Also I know the GM. I know the mu and Cox. So I can easily calculate the W by L ratio of the MOSFET 1 and 2. So the W by L ratio for MOS 1, which is basically 8.82. If I approximate it, that's basically the 9. Okay. After that, I have to calculate the W by L ratio for the MOS transistor 3 and 4. Transistor 3 and 4, this mean the PMOS M3 and N4. Before going to calculate the W by L ratio for N3 and N4, I have to know two parameter, which is basically the VTN minimum and VTP maximum. The maximum threshold voltage, the maximum threshold voltage for this PMOS, and the minimum threshold voltage for this NMOS. How to know that? How can I know that? To know the maximum threshold voltage for this PMOS, I have to set another arrangement in Cadence. You can see here is a PMOS and another PMOS, and I set the current source. If I set the current here is a 40 microampere, also this current source also, and I set the length is 500 nanometer and an arbitrary width. Basically, there is no strong effect for threshold voltage for this with this width of this PMOS transistor, so I can set any arbitrary width. So I set the 2 micron and I set a length which is basically the 500 nanometer. So after that, after set the DC analysis, here you can see the threshold voltage, which is basically the 300 59.34. So the maximum threshold voltage was the PMOS, which is basically 359.34. So if I approximate it, which is basically the 0.35 volt, and this is basically the millivolt range, 359.34, and this, if I approximate it in voltage range, so it will be 0.35 volt. For the maximum and minimum threshold voltage for the NMOS, I have to set this arrangement. So here I here I set a current source and another current source in the above of this NMOS transistor, and I set the length and width which I calculated before. You can see the length, W ratio is 9. If I set the same length, so I set 500 nanometer or zero point 0.5 micrometer, so our width will be 4.5 micrometer. So that's why I know the width of uh, NMOS transistor, so I have to set the width of this transistor. So if I set 4.5, for that I have to run the simulation. So after set the length to it, I have to set the ICMR value. So to extract the maximum threshold voltage, I have to set the maximum ICMR, which is basically 1.2. So the threshold voltage is 5 508.87. So the maximum threshold voltage is, so the maximum threshold voltage is 0.5. So if I calculate the minimum threshold voltage, so I have to set the minimum ICMR value, which is basically 0.75. So let's set to run the simulation. Right, the minimum threshold voltage for the NMOS, which is basically the 457.22. So 457. See, after get the minimum and max minimum threshold is for the NMOS and maximum threshold is for the PMOS. I can estimate the value for the W by L of M3 and M4. So I have to calculate the gate source to gate voltage to calculate the source to gate voltage, or where I have to subtract it VDD to ICMR maximum. Then I have to add the minimum threshold voltage for the NMOS. Then I get the uh, source to gate voltage, which is basically 1.04 volt. You can see here source to gate, which is basically 1.04 or 5. There will be a significant change. And then I have to estimate the WL ratio. How can I estimate that? I know the I3, which is basically 40 microampere. Then I know the mu p Cox. I know the source to gate voltage. I know the maximum threshold voltage for the PMOS. Then I can easily calculate the W by L3. So after calculation, I can easily get 0.69 approximately. This is 1. After that, I have to calculate the W by L ratio for M5 and M6. Before going to calculate it, I have to know the gate to source voltage for the NMOS. How can I know that? I know the current I3, which is basically the 40 microampere. I know the mu and Cox. I know the WL ratio for NMOS 1. The WL ratio for NMOS 1, which is basically 9, which I calculate before. 8 or 9. I know the maximum threshold voltage, which I calculate from the cadence. After that, I get the VGS1 0.6 volt. Then I have to know the VD set. To know the VD set, I have to subtract the VGS1 from the ICMR minimum. Then I get the VD set. After know the VD set, I can easily calculate the WL ratio for the NMOS 5 and 6. I know the 5 I5, which is basically uh, the 80 ampere. I know the mu and Cox. I know the VD set. Then I can easily calculate. If I put all this value, I can easily do the 53, 52. So this is basically the WL ratio and length and width parameter. The W by L, W by L. So if I say the L is 500 nanometer or zero point 0.5 W by L, if the W by L is 1, then I can easily estimate or calculate the W value. 1 into L, the W also 500 nanometer. So in the next part, I will show how to simulate it by using the Cadence Virtuoso platform. So thank you for watching this video.